Okay. So go to the folder and the drive C, walk into week 2, day 6. Okay, just open this file, double click it. Then we will continue looking at it. Okay, so I think so don't worry about the R script. I will share my R script after we finish this today's session. So I think we need to talk about t-tests a little bit, okay, pair t-tests. Because yesterday is a little bit confusing, okay? So anyway, what we will do is we will just delete everything and start again, okay? Okay, so first we are going to run everything, okay? So press Control R, Control A, and then run it. Okay, that's great. Now let's do the pair t-test, okay? Pair t-test. Okay, yesterday we encountered some errors because the problem with pair sample is that you need to have the same sample size for each group. Okay, so yesterday we tried with sex and it didn't work because sex we have 75 for female and 46 for male. Okay, and then okay, let's continue doing this. So in our data set, what way we use is we will assume, okay, this is assume test 1 and test 2 as before and after. Before and after. So this is what pair data is, okay? Anyway, independent data is. So when we look at the patient data codebook, we can see that test 1 is interleukin 6 and test 2 is CRP, okay? But we will assume that test 1 is before test and test 2 is after test, and we will compare it, okay? Okay, so right now, okay, so we have test 1 and test 2 already replaced with the we already replaced minus 99 with NA. Okay, so one way to do is we use X and Y. Okay, we use X and Y. So when we use X and Y, we didn't have any data argument, so we use with function. So with patient, and then we say the test. Then in X, we give it test 1, and Y, we give it test 2. Okay, so, and then we indicate that this data set is pair sample. Okay, so we run this this line of command. So you can see that we got the result. Okay, pair t-test. Okay, so in this case, we cannot do anything. So in this case, we cannot use the formula for t-test. Okay, so yesterday we looked at it, and there are two t-test function. The first one, this one, we use formula and data set. Okay, and for this one, we use X and Y, which is a different vector. Okay, so yesterday we tried it with this line of command. I think we did it like this. Okay, with age and Mary, I think. Not true. Okay. Okay. So anyway, this is what we did yesterday. It is wrong. Okay. It is wrong. Why it is wrong? Because when we use x and t test with x and y, okay, when we use x and y, x represent, okay, a should be equal to mean of group one, okay, whatever it is, okay. If it is married, then it is married group and unmarried group. So x should be the, sorry, a should be the age of, okay, let's write married, okay, age of married group. Then, and y should be age of unmarried group. Okay, so this is what it is wrong yesterday. So unmarried group. Okay, so here, when you use software, you need to understand that whatever you put it, if it is a number and if it can calculate, then it will produce a result, okay? Whether it is the right way or not, you have to decide, okay? You have to decide whether it is correct, it is the correct way to do this, okay? So here, I will show you the correct one for this one, okay? Because in pair data, it didn't work. It gave you an output, but this one is wrong, okay? Because in our patient data set, with age and married, when you're trying to use with the formula, then I think it didn't work, okay? Because we still have the same problem, because married and unmarried group do not have the same value. Okay, so why it works? Why it works? Because this line of code works because when you consider the sample size for age, it is 120, right? When you consider married, it is also 120. So they have the same sample size. So that's why there is no error there is no error in this code, but it is wrong, okay? So anyway, when you use X and Y, it should be group one and Y should be group two, whatever it is. Okay, so this is the wrong way. Okay, so the correct way is here, but it is not working because we do not have the same sample size. Okay, anyway, that is how to do pair t-test. Okay, this is the correct way of doing pair t-test. Okay, so in pair t-test you have two variable. Okay, you have two variable with the same sample size, or two group with the same sample size, then it will work. Okay, otherwise when you put when you categorize with something like this, I think this is how you code your data. Okay, it's a little bit different, but we won't spend time anymore here. Okay, so anyway, in your pair data set, the common way is you will encounter before and after, okay? Or anyway, there will be two variables, and then you specify X and Y, okay? If it is not two variable, but yes, okay. Okay, anyway, this one didn't work. Okay, this one didn't work. So yesterday we tried it, and I just want to explain that why even it gives you an output, why it is wrong. Okay. Okay. Anyway, let's continue with the recursion. Okay. So we also have the recursion test. Okay. So yesterday we said for the parametric test, we have a condition. Okay, we have condition. If condition for independent t-test does not match, what will we use? We use Mann-Whitney U-test. Okay, or we're calling Mann-Whitney U-test. Whitney U-test. Okay, and if it is dependent t-test, then we use we're calling rank sum test. Okay. Wait, I think it is sign rank test. Okay. Anyway, the idea is you have to specify whether it is dependent sample or not. Okay. So here we do not have any assumption. Okay, but you need to say that whether your observations are dependent on each other. If it is dependent, okay, and t-test conditions are not met, then you use Mann-Whitney U-test, where you specify pair in R code, pair is false. Okay, here pair is equal to true. Okay. Okay, so how do we run this? Let's try with cause. Okay, the function is with cause. So let's look at the will cause. So here we have the same formula data function. Okay, so we will use that. So what do we want to test? We want to test age and sex. Okay, so we will say that age versus sex. Then we specify data. Data should be patient. Okay, and then we say that it is not pair because it is independent t-test. Okay, we will set pair to false. Okay, so this will give us the p-value. Okay, so when we scroll up and look at this one, okay, independent t-test, and run this, we can see that p-values is not that different. Okay, because there is no age difference between male and female. Okay, essentially. So whether if the condition for t-test is met, then the p-value or the p-value for the Wilcoxon test and the t-test are not that different, are very close. Okay, anyway, where we greater than 0.05 or very close. Okay, so this is for the independent t-test. Okay, what about the dependent t-test? Okay, let's try and run this dependent t-test. So here we also use test 1 and test 2. Okay, because it works. So we will assume that test 1 and test 2 as before and after test. Before and after test. So test 1, well, the two variable, the two group will be dependent on each other. Okay, because one happened after another. So this is the idea of pair data. Anyway, so we will use this above function, x and y function. Okay, the function with x and y input. So we have to use with function to give it to specify data set, and then we say will cause dot test. Okay, and then we say x is equal to test 1 and y is equal to test 2, and then we have to specify pair is equal to true. Okay, so this is the Okay, spelling is important, right? So this is the Wilcoxon sign rank test, okay, for with the continuity operation, okay? So the two output, okay, let's clear this, okay? How do we clear this? We give it Control L, okay? We click here and give it Control L. And then we will run, compare the two outputs. Okay, so here, this is independent sample, so it calculates Wilcoxon rank sum test and give it a p-value, okay? Here, we give it pair is equal to true. So this is pair data, pair sample. So it calculates Wilcoxon sign rank test and give the p-value. Okay, so let's look at here. This is the pair t-test for test 1 and test 2, okay? And this one is Wilcoxon test for pair data. So essentially it's quite close, right? 0.05. So it means that the mean difference between test 1 and test 2 is different, okay? Considering that it is the pair data, dependent data. Okay, so we have the p-value for Wilcoxon test. Okay, any questions? Okay, if not, we will go to chi-square. Okay, so we will add a session, press Ctrl-Shift-R, and then we will write chi-square test. Okay, so in chi-square test, the same assumption is valid. Okay, the condition or assumption, we normally call it assumption. Okay, so it still should have independent assumption. Okay, it still should have the sample size assumption. Okay, so here we normally look at this is based. This is also taken from the sampling distribution and central limit theorem. So we should have sufficient sample size. So rule of thumb is 30, but we still have another condition, which is very important. Okay, what it is? So before we talk about this, let's try to look at the chi-square. Okay, how do we do chi-square? Okay, anyway, we were in this example we will use sex and married. Okay, which is easy. Okay, so we have male and female, and then married, not married group. So essentially, we creating the cross tabulation. Okay, so we will tabulate patient, and we put sex, and then cross tabulate. We cross tabulate by married. Okay, so this is how you do it. Okay, so now we have the contingency table. Okay, okay. So anyway, we won't go into detailed calculation of chi-square, but essentially what they did is previously we talked about in probability session, we talked about the conditional probability and marginal probability. Okay, so the same here. So how do we do this? We have the probability and percentage is the same. Okay, the way you interpret is this different, but the number are the same. So here, based on this percentage, okay, based on this percentage, what we can do is we create the expected value based on the percentage. Okay, so here we have different number. So based on the percentage, we calculate different value. That is called the expected value. Okay, what we have here is observed value, and then we subtract the two table. Okay, this table and then the table with the expected value, and then we got the chi-square. Okay, if you want to read the detailed calculation, you can just go to the Wikipedia and then read it. They have very nice explanation of how chi-square works. Okay, So anyway, that is what they do. Okay. So tabulation, this tab command function from Amstrad also produce chi-square and exact Fisher exact test at the same time. Okay. Okay. What I'm going to do is what I want to say is the third condition is these are called cell. Okay, like Microsoft Excel spreadsheet. Okay, these are called individual cell. So these individual value should be greater than 5. Okay, so these each cell must be greater than 5. Okay, so here we have any. Okay, so we just remove any dot in. We will remove missing value. Okay, so that's any dot in. Okay, so anyway, whether you remove any or not, the any is not counted in the chi-square calculation. Okay, so anyway, chi-square value does not change. So here it means that this is called we just say simply chi-square test, right? But essentially this is the chi-square test of independence. Okay, there are 3 chi-square tests. Chi-square test of homogeneity, and this one, chi-square test of independence, and chi-square test of goodness of fit. Okay. So what we are doing now is chi-square test of independence. So we are looking at 2 categorical variables and see if they are dependent of each other. Okay, and trying to look at the p-value. So p-value is 0.05. So saying that there is no difference between sex and marriage. Okay, sex and marriage. Okay, so you got it, right? So these are 3 assumptions. Say in our example we have one value less than 5. Okay, and then you need to calculate. You need to look at the exact value. So anyway, when assumptions are correct or satisfied, then you will get very similar conclusion. Okay, whether you use chi-square or exact value. So exact is the Fisher exact test, which based on the exact calculation of the approximation to normal distribution. Okay, this is the chi-square distribution, which is an approximation to normal distribution. Okay, which is this test is accounted for the lower sample size, or one cell value is less than 5. Okay. Okay. Anyway, these are the conditions, and this is how you interpret chi-square. So here we have this p-value greater than 0.05. So we say that sex and marital status are not associated with each other. Okay, so this is how you calculate chi-square and exact test in Amstrad using function from Amstrad. Okay, what about we use base R? Okay, base R is a little bit different. Okay, so you can look at the chi-sq.test. Okay, that is the Pearson chi-square test for count data. So it only have one x and y value and without data argument. So we have to use with. Okay. So here we specify data set and then say chi-sq.test, and then we specify age, what is age, sex, and y is married. Okay. Okay, and then so when you do this, based on by default included the Yates continuity correlation, okay, which we don't want because I mean the conditions are not violated. Okay, there is no cell value less than 5. Okay, if cells is less than 5, one way you can continue using chi-square is with the Yates continuity correlation. Okay, which adjusted for lower sample size. Anyway, so we need to say that correct is equal to false. Okay. Okay. So now, okay. So it's a little bit when you look at these two values, it's the same. Okay. So you need to understand what is being implemented behind the scene and how you can make use of it. Okay, so this is how you do chi-square test. Okay, and the same can be, I mean, the same for Fisher AZ test. Okay, it is R.A. Fisher. I think he developed this method, so it's named after him. Anyway, this is the AZ method. Okay, AZ test. So we use the same. Okay, we specify the data set and then we say AZ. Okay, not AZ. I think Fisher.test. Okay, and then the same, X should be sex and Y should be married. Okay, let's see. Okay, so here Fisher is a test. Basically, what it did, what it did is they trying to behind the scene they trying to simulate. I mean, they trying to run multiple simulation. Okay, and then come up with the p-value, which is quite close to our p-value. Okay, I mean, the same conclusion, not very close, the same conclusion. Okay, so let's see Fisher.test. Okay, here what we have is one thing. Okay, simulate p-value false. Okay, because sometimes when you have a very peculiar values, then you will have to simulate your p-value. Okay, to get the output. So we will say that simulate dot p dot value is equal to true. Okay. Okay, so in this case, not the same, because Fisher is a test. So the question is, Fisher is a test and Yates continuity correction are they the same? So no, they are not the same. Okay, so Yates continuity correction just, you know, make some adjustment to the formula for chi-square test. Okay, so Fisher is that is a different formula. Okay, this is, so the two are different. Okay, anyway, here we don't have any changes in p-value, but sometimes when you fail to when this function fails to give you an output, then you just put the simulate.p.value is equal to true. Okay, so it will give you a simulation for p-value and then come up with a p-value. Otherwise, you will get an error. Okay, so sometimes it is like that. Okay, so this is a chi-square, and then the opposite is for Fisher AZ test. And then there is a test called McNemar test. Okay, McNemar test is basically for the ordinal data. Okay, so in categorical variable we have what we have is we have nominal and ordinal. Okay, so with order and without order. So if there is no order, like in our case, male and female, there is no order. Okay, then we use chi-square or Fisher AZ test. Okay, so with order, you can still use chi-square test, or if the conditions are not met, then you cannot use Fisher AZ test. You have to use McNemar test. Okay, McNemar test. Okay, I think McNemar.test. So this is the McNemar chi-square test or count data. Okay. Okay, so how do we use? We can still use X and Y. Okay, so okay, for the demonstration purpose, let's use sex and marry. Okay, So I think, okay, let's see. Maxima dot test h is equal, y is equal to Mary. Okay, and let's run. Okay, it works, right? But as you can see, okay, this is with continuity correction, so we don't want it now. So anyway, should be correct, false. Okay, anyway, without correction, p-value is less than with correction, right? So you have to remember that any adjustment made to the formula, you will get a slightly larger p-value, okay, for the chi-square or for the maxima test. Okay, so I think we have a p-value of the same variable. But okay, let's look at this chi-square and let's look at this maxima. Okay, so this one we for the two tests we use the same variable. Okay, sex and Mary. But for Pearson chi-square we got a p-value of this one, and for the maxima test we have the p-value very significant, right? So that's why you need to understand that the condition or the situation where you should use which test. Okay, so for chi-square test, when you have the categorical variable, you can use chi-square test. But when your data, when your variable is ordinary variable, using maxima chi-square test is more correct. Okay, other than a Pearson. Okay, anyway, this is for the categorical data. Okay, so before we continue with the ANOVA, let's try using quickly with a correlation. Okay, so we do correlation, then we will use what do we use? Test 1 and test 2. Okay, again, because these two can be correlated. So first we will find correlation. Okay, not p-value yet. We will find a correlation. So we already did this. Okay, so we use with function because there is no data argument in correlation function. So we specify data set and we call. Okay, so this is the correlation, and we say test 1 and test 2. And you can write x and y, x equal to test 1, x equal to y equal to test 2. Okay, that's up to you. And again, we also said that we have to remove the we have to remove missing value. Okay, so that's why we will say complete obs. Okay, complete observation. So we have two variables, test 1 and test 2. Okay, if test 1 is missing, then it will remove. Okay, that patient will be removed. If test any variable is missing, then it will be removed. Okay, so we will only use complete data set, complete value in both variables. Okay, then we will test the correlation. Test for correlation. So we mention, okay, patient data set, and then we say call.test. Okay, so this is the test for correlation, and then we say test 1 and test 2. Okay, so this is the Pearson product movement correlation, and test 1 and test 2, and the p-value is not significant. Okay, so anyway, we got the same correlation. Okay, here. So basically, our null hypothesis is the correlation is equal to 0. Okay, null hypothesis, there is no association or there is no correlation between the two variables. Our alternative hypothesis, is there's true correlation which is greater than 0, which is not equal to 0, okay, which is not equal to 0, but our p-value, look at our p-value, which is greater than 0.05. So we say that, okay, there is no enough evidence to reject the null hypothesis, okay. This is the correlation. Okay. So any questions so far? So we finished t-test, chi-square, and correlation. And then we will look at the ANOVA, okay?
No, can you please repeat the interpretation for a correlation test?
This one?
So,
okay, so p-value is greater than 0.05. So we cannot, there is no enough evidence to reject the null hypothesis. So which means that there is no correlation between test 1 and test 2.
though we have the code test in the previous command in 151 line, we have, what is that?
But this one is correlation. This one is
Okay,
correlation value. So how do we interpret this? Okay, so correlation value range between -1 and +1. Okay, so this is very close to 0. So we say that, okay, there is no correlation.
Okay.
But we don't know. We don't know because we got this result due to chance. Okay, this result happens simply due to chance. So that's why we did a statistical testing, hypothesis testing.
Okay.
Okay. This one is not a hypothesis test. This one is just calculate the correlation value, which is similar as this one. Okay. The same value.
That means if for the first test, like only for core, if the value is not that high, the correlation between two variables are not high, then we don't. Is it necessary to run core test?
It's not necessary.
It's not necessary.
I just want to recall that we can run this. But anyway, when you run the core test, we will have the correlation value anyhow. So. Okay, so I think time is 40-minute time is up, so we will stop this and then. It's really nice, huh? To all doctors and nurses and medical workers. Thank you. Okay. I think this is from Thailand. Okay, anyway. Okay, yeah, I just want to show you that. Okay, let's find t-test. Okay, and then look at the Wikipedia. Look at the Wikipedia. It's a little bit. Sometimes I think those who wrote this page for this page for t-test are mathematicians or maybe statisticians, so it's a little bit difficult to understand, but I think you will appreciate if you read it, okay, history, and there is this one, okay, William Seeley Gossett, who initially works in the beer company, right? So he brew alcohol, and so because he cannot, so he was doing a lot of experiment with beer alcohol, but he only got a small sample size, okay, because he cannot because his company does not give him a lot of maybe a lot of budgets or a lot of sample to experiment with, so he got small sample size. So he came up with a T distribution, student distribution, which is the pen name, I think, which is a pseudonym, and published T statistics. Okay, Claudie Guinness, which is the brand for the what I think it is the alcohol company. So it's really amazing how these people trying to come up with different strategy to tackle their difficulties. Anyway, we have one sample test, two sample tests, which is phenomenally amazing to get these kind of, I mean, to get this kind of conclusion based on the data. So this is how you calculate T. Okay, test statistics, which previously we calculated with z-score. Okay, the same formula. So we got observation minus population mean divided by standard deviation square root of n. Okay, so you can read it if you want to know in detail. Otherwise, or ordinance is when you use the test and how to run it in software and how to interpret. Okay, so you can calculate manually using our data set. Okay, this is how you calculate standard deviation, but which I'm not going to talk in detail. Okay, so it's quite interesting. So this is how you calculate pair t-test. Okay, the formula is the same, but to calculate standard error is a little bit different. And so when we got unequal variances, we try to calculate this one. Okay, separate standard deviation and separate sample size, and that's square root of the sum of these two values. And then with equal variances, we just pool standard deviation. Anyway, these are very detailed, and you don't need to understand to interpret the result. Okay. Okay. Anyway, you can look up all test statistics. Okay, hypothesis test, and it's very interesting. Okay, we will switch back to RStudio and continue with the ANOVA. Okay, so let's go with the ANOVA. ANOVA, which is the analysis of variance. Okay, analysis of variance. Okay. Anyway, when we talk about t-test and when we talk about the Wilcoxon test, what do? We compare two means. Okay. To simply put, we compare two means. And here, we will compare, okay? We will compare, this is analysis of variance. So we won't compare mean, we will compare variances, okay? Of different groups, or several groups, multiple groups, or however you call it. And they should be equal, group greater than 2, okay? If it is less than or equal to, then we use t-test. If it is greater than 2, then we use ANOVA. Okay, it is how it works. So ANOVA, what do we do with ANOVA? We compare variances. Okay, so there are two kinds of variances. Okay, for each group, there is this variance or intravariance. Okay, to make it simple. This is basically standard deviation. This can be similar to the standard deviation of each group. Okay, the same. And then what do we have? We have variances for the whole group. Okay, before we go to the whole group, we have standard deviation. Okay, we have variances for each group. Okay, this one is within the group. Okay, so this is is within variance, within group variance. Okay, within group variance. This is between group variance. So say we have 3 groups. Okay, say we have smoking, non-smoking, current smoking, former smoking, and no smoking. So we have 3 groups. And then what can we do? We can find standard deviation for each group. and then compare this variances between these groups. When we look at the standard deviation of each group, it is called the within group or intra-group variances. Okay. When we compare three groups, okay, current, former, and no smoking, and then we compare the variances, okay, and then this is called the between group variances. Between group variances, and then we have the whole variances for the whole sample size. Okay, variance for the whole sample size. Okay, based on this, based on this, we calculate F-test. Okay, F-test statistics. Okay, like I said, if you want to know detailed calculation, then you look at the Wikipedia page. It contains formula. Okay, so basically using this using this variances, we calculate F-test and then produce a p-value. So basically that is the ANOVA. Okay, but what does this p-value mean? Okay, what does this p-value mean? So okay, so for smoking we have current, former, and then we have narrow smoker group, and then we compare, say, the age. Okay, age and smoking. So age among these three groups, we found p-value less than 0.05, and what does it mean is that there is a difference. Okay, the mean between these three groups is different. Okay, ANOVA cannot tell you which one is different. Okay, it will tell you there is a difference, but ANOVA does not know which one is different. Okay, so that's why this is the overall p-value. So when we test ANOVA, we know that p-value, if p-value is significant, there is a difference. We don't know which one and which one. Okay, so how do we compare? We compare current versus former, okay, and then former versus never, and then current versus never. Okay, so basically that is the comparison. So you may ask that, okay, so why don't we do t-test? Okay, why don't we do t-test for this one? Why don't we do t-test for separately for each comparison? You can do that. Okay, you can do that, but each time you do this, okay, for each, so why not use t-test separately? You can do that, but each time we use t-test, there is an alpha error. Remember, there is an alpha error. So how much we set normally? 5%. Okay, and then when you add, when you combine all these, for this one, for this one, for this one, alpha error will increase. Okay, alpha will increase if we use separately. So anyway, that is fine. One way to walk around is we can use by adjusting the p-value so we can combine these three p-value, okay, for each comparison, and adjust with Bonfario correction. But anyway, there is out of this code. Okay, I just want to let you know that so you have groups, okay, multiple groups. You can make comparison for each category, for each groups, and then use the t-test separately. And you need to adjust the p-value. That is bothersome, right? So we can just directly use ANOVA. Okay. Okay. So we can use ANOVA. So let's look at the ANOVA command. Okay. ANOVA command is the not ANOVA, it's AOV. Okay. So we will fit an analysis of variance model. Okay, so basically ANOVA is the it's the very simplified form of the linear regression. Okay, so how do we do this? We will use smoking, right? So but first we need to fix the smoking. So let's look at the smoking HS. Okay, smoking HS variable. So we have minus 99. Okay, so we will fix this above in the data management section. So we will replace smoking HS and smoking HS if equal to minus 99. Okay, so we change something in the way above. So what do we need to do? We need to run everything. So we say Control A, okay, and then run everything again. So this is to make sure that our code works. Okay, we need to run up and down, top to bottom. Okay, anyway, we got our smoking HS fixed. So we will look at the ANOVA. Okay, so when we look at the ANOVA function, there is the data argument. Okay, so we don't need to use width. So fit ANOVA, and then we say that okay, in AOV, and then we say age. Okay, so this is a formula. So how do we define formula? We say with a tilde sign. Okay, we specify with a tilde sign. You can find the tilde sign above the tab key or escape key on your keyboard. And then we say smoking HS. Then we say data should be coming from patient data set. Okay, that's it. So you can, there are other arguments, but right now we don't need it. Okay. So when we fit our data set into variable into ANOVA model, analysis of variance model, this is what it gives. Okay, there are sum of square and degree of freedom. Okay, so when you follow the detailed calculation, you will understand what this means. Okay, so like in our calculation of standard deviation, which is coming from variance. Okay, with variance is called the sum of square. Okay, sum of square of deviation. That is called standard deviation, right? So deviated from where? Deviated from the mean, right? So we have sum of square, and then we have degree of freedom. Okay, so we have to simply put, okay, to simply put, we have variances, okay, deviated from a mean. So smoking HS account for 211, while the residual, which means that we don't know anything about it. Okay, we don't know anything about it. But smoking HS can only account for 211, and residual is 4,000. Okay, and then we see there are 2 degrees of freedom because we have 2 variables anyway, and then residual standard error. Okay, and you see we have 7 observations deleted due to missing value. Okay, I think one observation in age and 6 observation from smoking HS. Okay, anyway, this is how you fit ANOVA. So where is p-value, right? So in order to get a p-value, what you need to do is you need to put it to summary. Okay, so we cannot do that. So we need to put this result to the, say, how to, okay, ANOVA dot, we will name it. Okay, we will give it a name. So ANOVA dot smoking. Okay, it's a little bit long, but, and then we will run it. So you can see now that we have the under data, we have ANOVA dot smoking, which is a list. Okay, which is not a data set. If it is a data set, it will give you variable and observation. Okay, so we have a list. Okay, so right now, don't worry about the list. Okay, in order to get a p-value, you just need to say summary. Okay, ANOVA.smoking. So we need to look at the summary of this model. Okay, this ANOVA model. Okay, now we got 0.05. So it's approximately, what do you say, on a margin, okay? On a margin of significance, 0.05. Okay, so this is how you do ANOVA in R. Okay, say our p-value is significant, and like I said before, when you do an ANOVA, we know that there is a difference. Okay, so if our p-value, so in this case 0.05, which means that there is no enough evidence, so we reject the null hypothesis. So what is the null hypothesis here? Okay, null hypothesis is there is no difference between groups. Okay, an alternative hypothesis is there is a difference, and we don't know which one is different from which. Okay, there is a difference. So we have three groups which we can compare in three ways. Okay, but we don't know which one is different. We got p-value. Say if this p-value is less than 0.05, there is a difference. And if we want to know the difference, then there are certain ways to look at the comparison of this way. Okay, so that is called the post ad hoc test. I think post hoc test. Anyway, it's not important. Okay, the name is Chuki HSD. Okay, so you can look at this Chuki HSD. Okay, so which computes the Chuki honest significant differences. Okay, so how do we do this? You just put the model here. Okay, you just put the ANOVA model here. So we will say that Chuki HSD, and then we say ANOVA.smoking. Okay, so as you can see, okay, what do we fit? We fit this formula. Okay, and what is the result? The result is the effect size. Okay, there is a difference. So this is the effect size, and we got 95% CI for the difference. Okay, so what do? They look at the differences between variances, and then look at the the 95% CI and p-value. Okay, so in this case, our original ANOVA model is not significant. So these data were not significant. I just want to demonstrate how you do the ad hoc test. Okay, so this is called a multiple comparison of means. Okay, so we compare former group versus current group, never versus current group, and never versus former group. And this one is only marginally significant, and the rest are not significant. Okay, never and current is marginally significant. So we can say 0.05, so that's not too bad. Okay, anyway, so this is how you fit an ANOVA test, and this is also how you look at different comparison group and their p-value. Okay. Okay, so next, before we go on, I think we need to say something about the condition, right? Okay, so there are three to use ANOVA, there are three conditions. Okay, and the same as above. Okay, number one is independence, same. Okay, so these groups should be independent. And second is normality test. Okay, so you should test the normality test, so which we already did H. But again, let's see. Okay, let's see for H versus smoking HS, and we look at the normality. Okay, check normality. So you can create histogram, or you can just look at sum, that group summary measure. So we um, produce a summary measure or age group by smoking HS. Okay, so p-value for each category is normal. Okay, p-value is greater than 0.05. So we say this normality assumption is correct. Independent assumption, we say that it is correct. Okay, one group does not depend on another group. Okay, next we need to look at the variances. Okay, wait. Wait a minute. Yes. So the third assumption is the same, right? The homogeneity of variances. Okay, variances should be the same. Homogeneity. Okay, that's a little bit different to understand. Difficult to understand. So we say that equality of variances between groups. Okay. There is homogeneity of variances, which means that the variances between groups should be approximately equal. Okay. Okay. Anyway, I think we can test using this Vato test from our previous t-test, right? So let's look at this Vato test. I think we can only say two group. Let's try this. Okay, Vato test, and then we say H. Well, we will put formula and then data. Okay, so we will say H, and then we will say smoking HS, and then data is equal to it is. We will check normality. Sorry, we will check variances. If variance is high. Yes, we need to have two level. So wait a minute. How? Okay. So here, so we cannot we can only use two groups at a time. So we cannot use this. Okay. So what we have to use is called Bartlett test. Okay. I think Bartlett. Okay, Bartlett test. Okay. So this is Bartlett test for homogeneity of variances. Okay. So this is Bartlett test. So we will use this, okay, Bartlett test formula and data. Bartlett test, and then we say H, then field sign, and we say smoking HS, and then data is patient. Okay. Okay. So now it is also a hypothesis test. Okay. So the null hypothesis is the variances are equal. Alternative hypothesis is not equal. Okay, so it used k-square, okay? So a little bit different. And degree of freedom is 2. And p-value, because we compare two groups, so anyway, p-value 0.4049. Okay, so basically we will say that variances are equal. Okay, and variances assumptions are not violated. It's not violated. So we can use the result for the ANOVA test. Okay, and then if p-value is significant, we can do the I think. Okay, anyway, this post comparison test. Okay, we'll say this is a comparison test. This is a comparison test using 2K HST, and then you look at which one is significant. Okay, which comparison is significant. So this is how you do ANOVA in R. Okay. Anyway, so if these conditions are not met, okay, are not satisfied. So what then? What do we use? We use Kruskal-Wallis, okay? Kruskal-Wallis test. This test. Kruskal test, okay? Kruskal-Wallis rank sum test. So you can see here it is a rank sum test, okay? In t-test, with the alternative non-parametric test is rank sum test or sign rank test. Okay, so basically what is the difference? The difference between parametric and non-parametric is like I said yesterday, in parametric test we use parameter, okay, population parameter and no population parameter, which is a standard normative distribution, standard normative distribution. So in this case, in the non-parametric test, what do? We order value, okay, in 2 groups or 3 groups, and then we rank them, okay. So we give it an order and then rank 1, 2, 3, 4, 5, 6, and then divide it into corresponding groups, and then combine and calculate the ranks, okay, not the actual value. We work with the rank value. Okay, anyway, so that's why it is called the non-parametric test. So there is no parameter. We just use the rank, and we compare that. Okay, for Wilcoxon test, there is no difference in rank between the 2 groups, and then in this Kruskal-Wallis test, the same. Okay, so anyway, if the conditions are not satisfied, then we use Kruskal-Wallis, which is the same as, I think we can use this one, okay, formula data. Okay, say Kruskal.test, and then we have age, and then we have to put formula, okay? So you look at the usage and put accordingly. So we give it age and then tilde sign, give it HS, okay, categorical variable, and then data is patient. Okay, so I think that's it. And then we got the p-value. So as you can see that, okay, so this is the case. So when we run the ANOVA, p-value is not significant, okay? But when you run the Kruskal-Wallis test, p-value is significant, which is barely significant, okay? 0.05, 0.03, which is only 2 decimal point difference from 0.05. So you need to determine which p-value you have to use, okay? So that's why first, always use parametric test, okay? Because we compared it to the known population distribution, known distribution with the parameter. So it is more powerful and less biased, okay? So that's why priority is use parametric test. but we need to check the conditions or assumptions. If the assumptions or conditions are not satisfied or violated, and then we need to consider this, okay? We need to consider non-parametric test. So that is the flow you need to follow, okay? So that you don't confuse which p-value you have to use, okay? Because as someone who is doing analysis, you always want two variables to be statistically significant, okay? So you are happy when you find a p-value less than 0.05. So don't be tempted, okay, in this case. So you have to use this ANOVA test because we check the assumptions are correct, okay? Okay, anyway, this is a demonstration of how you use Crystal-Wallace test. Okay, where do you get an error? Which one, Crystal-Wallace or?
Yes, in Wallace test.
Okay, did you remove -99 data?
Yes, I think.
And so what did the error say?
All group levels must be finite.
Okay, should be finite. So I think, so did you remove okay, did you replace the age value?
Age,
Did you change this? Age value and smoking ages?
Yes, I have changed it.
Okay. Can you share your screen? Let's look at your screen. I think this is the end of the, inferential statistics. Okay, this is the commonly used traditional hypothesis test. Okay, for other tests, if you need it, then you need to, okay, can you share it, your screen? If it is possible, because we're using the same data set. Is there anybody who got an error? Okay, so can you go down? Okay, can you go down? Okay, so can you do the codebook patient? It should be fine, right? And because smoking ages, smoking ages 6. Cholesterol. Oh, interesting. Can you run everything again? So I think it should work. Can you Control A? No. Can you press Control A and then run everything? She works. Oops. It's very interesting, huh? Can you change it to BMI and see if it works? Can you change the second one from age to BMI? I don't see any spelling error or anything. All group levels must be finite. No. I mean from age to BMI. Okay, interesting. Okay, so what is the version of R? I think you can check version something. I think you can check version. type version in a console.
Okay. From where console?
And yes, in a console,
What's
type version,
what?
VRSI1 version. I think mine is 3.6.2. Yours version is 3.5.1. Maybe that is the reason. Okay, because we are using different
Okay.
version. So I think that explain it. Okay, I think I'm using 3.6.2. Okay, so 3.6.2 2019 version. Because this should work. Okay, because we are using um, the same data set. So anyway, I'm going to share the script. So perhaps you can try, you know, you can try with my script and see if the error persists. Okay, if the error is still there, I think the recommended way is to fix is to upgrade your R. Okay, so uninstall R and then download 3.6. I mean 3.6, at least 3.6, and then try it again. Because different version, they fix a lot of bugs issues. So I think that may be one of the bugs they already fixed in 3.6.2, but not in 3.5. So maybe that's the reason. Okay. Okay. Anyway, if you have any questions, you can message me or post it on a Facebook group. And I think this is the end. Okay, for inferential statistics. And tomorrow we will continue with the linear regression, and also we will add some data management too. Okay. Okay. So see you tomorrow. Stay safe.